Hello, viewers. In today's class, we are going to discuss yet another important problem from integrals, right? And in this class, we'll discuss this integral using the concept of beta function, right? So the beta function is also known as Eulerian integral of first kind, right? So here we have to solve this integral that is from 0 to 1, and the integrand is 1 minus square root of x raised to 8, right? So in this lecture we'll see a beautiful application of beta function to evaluate this type of integral, right? So let us start. So let us call this integral as I, right? So here what we will do, we'll make use of that method of substitution, right? So let us substitute square root of x as y, right? So y is now y square is equal to x, right? So let us differentiate both sides. So dy square is equal to dx, so we have 2y, dy is equal to dx, right? Now let us change the limits, right? So here x varies from 0 to 1. So when x is 0, then the value of y can be calculated from this relation. So y is equal to square root of 0, that is equal to 0. And when x is equal to 1, then the value of y is square root of 1, that is simply 1, right? So when x goes from 0 to 1, then y goes from 0 to 1. So now let us express this integral in terms of this new variable y, right? So now we can write I is equal to 0 to 1. We have 1 minus square root of x, which is replaced by y, and we have here the power 8, and dx is replaced by 2y dy, right? Okay, so now this 2 can be it can be taken out outside the integral. So we have 2, 0 to 1, 1 minus y raised to 8, and we are left with only y, right? So now we can express this integral as 0 to 1, and here we have y raised to 1. So y raised to 1 can be written as 2 minus 1, right? And 1 minus y raised to 8 can be written as 9 minus 1, right? So we have written this integral in this form in order to convert it into a beta function. Now see, the beta function, that is beta mn, is defined by this integral, that is 0 to 1, and we have say x raised to m minus 1 and 1 minus x raised to n minus 1 dx, right? Where m and n are greater than 0, right? So this integral is known as beta function, or the Eulerian integral of first kind. And here we see that this integral is similar to this one, right? Except the variable. So here we have y and here we have x. And see, if we compare this integral with this one, then see the value of m is 2, right? So this is m, and here we have 1 minus x, here we have 1 minus y, and the value of n is 9, right? So we have now this integral, that is 0 to 1, y raised to 2 minus 1, 1 minus y raised to 9 minus 1 dy is equal to beta of mn. So here we have beta, m is 2 and n is 9, right? So now this integral I can be written as 2 times, here we have 2 a factor, and then we have beta of 2 comma 9, right? So now we know that an important relation between the beta function and the gamma function, beta mn, is given by gamma of m, then gamma of n, and divided by gamma of m plus n, right? Where m and n are greater than 0, right? So here we have m is equal to 2 and n is equal to 9. So using this relation, we can write beta 2 comma 9 as gamma of 2, gamma of 9, and then we have gamma of 2 plus 9, right? So now we can write this integral I as 2 times gamma of 2, and we know that gamma of n is defined as, that is gamma of n plus 1 is defined as n factorial, right? Where n belongs to the set of natural numbers, right? So here, so when n belongs to the set of natural numbers, then gamma of n plus 1 is equal to n factorial. So here we have gamma of 2, right? So gamma of 2 can be written as 1 factorial, and then gamma of 9 can be written as 8 factorial, and in the denominator we have gamma of 11, and gamma 11 can be written as, here 1 factorial is 1, 8 factorial, and then gamma of 11 is equal to 10 factorial due to this relation, right? So now we can write 2 times 1 times 8 factorial. 10 factorial can be written as 10 times 9 times 8 factorial. 8 factorial and 8 factorial get cancelled. Here we have 2 5s are 10. So we have 1 over 5 times 9, that is equal to 1 over 45, right? So the value of this integral is equal to 1 over 45, right? Hello viewers, in today's class we are going to discuss yet another important problem from integrals, right? So in this class we'll solve this important integral using the concept of beta function, right? And beta function is also known as Eulerian integral of first kind, right? So we'll see a very beautiful application of beta function, how to evaluate this type of integrals, right? So let us start. So let us call this integral as I, right? So here we have the integral 0 to pi x square divided by square root of pi minus x dx, right? So here what we will do, we'll first make use of the method of substitution, right? So what we will do, let us first take in the denominator, we'll take pi as common, right? So we have pi 1 minus x over pi, right? So this is the first step. So now we can write it as 0 to pi. Here we have x square, and we can take square root of pi like this, and then we have square root of 1 minus x over pi, right? Okay, now let us rewrite this integral as 1 over square root of pi, and then we have 0 to pi and x square, and let us take this term to the numerator. So we can write 1 minus x over pi raised to minus half, right? Because this is square root, this is 1 over 2 power, so we can take it to the numerator. So this is minus 1 over 2. So now let us make the use of substitution method. and let us take y is equal to x over pi, right? So we'll take x over pi as y. So this implies that x is equal to pi y, right? And here we see that the value of x varies from 0 to pi. So we have x is equal to pi y. So dx is equal to pi dy, right? And we can change the limits accordingly. So when x is equal to 0, then the value of y can be obtained by taking x is equal to 0 in this relation. So we have y is equal to 0 over pi, that is equal to 0. And when x is equal to pi, then we have y is equal to pi over pi, that is equal to 1, right? So when x goes from 0 to pi, y goes from 0 to 1. So now we can rewrite this integral in terms of this variable y as 1 over square root of pi. Then we have 0 to 1, and x can be replaced by pi y. So we have pi y square, and then we have 1 minus y and raised to minus 1 over 2, and dx can be replaced by pi dy, right? So let us arrange the terms here. So we have 1 over root pi, and see here we have pi square and here we have pi, right? So pi square times pi is pi cube. We can take pi cube outside the integral sign. Then we have 0 to 1, and here we have y square, and then we have 1 minus y raised to minus half, and here we have dy, right? So now let us again rearrange this integral. So we have I, here we have pi cube, here we have square root of pi, which is pi raised to half. So now we can write pi raised to 3 minus half, and we have 0 to 1. Y square can be written as y raised to 3 minus 1, right? Because 3 minus 1 is 2, and here we have 1 minus y, and here we have power minus 1 over 2. The exponent is minus 1 over 2, that is half minus 1, right? So we have written this integral in this form because we are going to use the definition of beta function, right? So the beta function is defined as beta mn as 0 to 1, that is x raised to m minus 1, 1 minus x raised to n minus 1 dx, right? So if we compare this integral with this one, then we see that the value of m is equal to 3 and the value of n is equal to half, right? So n is half. So now we have I pi raised to, this is 3 to the 6, 6 minus 1, 5. So we have pi raised to 5 by 2, and this integral is now written as beta, and here we have mn. So m is 3 and n is half, right? Now let us make use of one important relation between beta function and gamma function, right? Now see, beta of mn is defined as gamma of m multiplied gamma of n divided by gamma of m plus n, right? Where m and n are both greater than 0. Right, so here we have m is equal to 3, n is equal to half, and 3 and half are both greater than 0, right? So now due to this relation, we have pi raised to 5 by 2, and here we have gamma of 3, then we have gamma of half, then we have gamma of 3 plus half, right? So this is pi raised to 5 by 2, gamma of 3, gamma of half, and here we have gamma of 5 by 2, sorry, here we have 3 to the 6, 6 plus 1, 7, right? So we have gamma of 7 over 2. So now let us write the values of gamma of 3 and gamma of 7 by 2, right? So gamma of 3 is equal to 2 factorial, right? Because we know that gamma of n plus 1 is equal to n factorial when n belongs to the set of natural numbers, right? Or when n is 0, then we have gamma of 1 is equal to 1 factorial, that is 0 factorial, that is equal to 1, right? So using this relation, we have gamma of 3 is equal to 2 factorial, which is equal to 2, right? And using an important relation, that is gamma of n plus 1 is equal to n times gamma of n, we can write gamma of 7 by 2 as 5 by 2 times 3 by 2 times half, and then we have gamma of half, right? Due to this result. So now this integral I can be written as, here we have pi raised to 5 by 2, gamma of 3 is equal to 2 factorial, and here we have gamma of half, and in the denominator we have gamma of 7 by 2, and due to this result, gamma of 7 by 2 is equal to 5 by 2 times 3 by 2. Here we have half, then we have gamma of half, right? So we know that gamma of half is equal to square root of pi, right? So these two terms get cancelled. So now we have pi raised to 5 by 2. 2 factorial is 2. Here we have 15 divided by 8, right? 5 3s are 15. 2 times 2 times 2 is 8. And we have pi raised to 5 by 2. 2 times 8 divided by 15, right? So taking this 8 to the numerator. So we have 2 8s are 16. So we have 16 times pi raised to 5 by 2 divided by 15, right? So the value of this integral is equal to 16 over 15 times pi raised to 5 by 2. So viewers, this is how by the application of beta function, we can evaluate these kind of integrals. Hello viewers, in today's class we are going to discuss yet another important and very conceptual problem from integrals using the concept of beta functions, right? So in this lecture we are going to find out the value of this integral using the concept of beta function, right? So here we have to evaluate the integral 0 to 4, and the integrand is x raised to 4 times square root of 16 minus x square, right? So let us call this integral as I, right? So let us start. So viewers, what we will do here, we'll make use of the method of substitution, right? So first we'll write this integral as 0 to 4 x raised to 4, and we'll take this 16 common like this, that is 16 1 minus x square over 16, right? And then we can take the square root of 16, and the square root of 16 is 4. We can take 4 outside the integral sign, right? So we have 0 to 4 x raised to 4, and here we have square root of 1 minus x square over 16, right? Okay, so now we'll make use of the method of substitution, and we'll take y is equal to x square over 16, right? So we'll introduce a variable, that is y, which is equal to x square over 16. So now we can write x square is equal to 16 y, and we can also write x is equal to 4 times square root of y, right? So taking the square root of 16y, we have 4 times square root of y, right? Okay, now let us differentiate both sides with respect to y. So we have dx over dy is equal to 4 times the derivative of square root of y with respect to y, right? So this is 4 times the the derivative of square root of y is 1 over 2 times square root of y, right? So this is 2 to the 4, so we have 2 over square root of y, right? So now we have dx over dy is equal to 2 over square root of y. So now we can write dx is equal to 2 over square root of y and dy, or in other words we can also write it like this: 2 times y raised to minus half, and here we have dy, right? So for this dx we have 2 times y raised to minus half dy. So now let us change the limits. So here we have x is equal to 0, and the upper limit is 4. So when x is equal to 0, then we can find out the value of y from this relation. So y is 0 square over 16, that is 0. And when x is 4, we have y is equal to 4 square over 16, that is 16 over 16, that is equal to 1, right? So when x goes from 0 to 4, y goes from 0 to 1. So now we can write this integral in terms of y, right? So we have 4, then we have 0 to 1, and x raised to 4, right? See, x square is 16y. So we have x raised to 4 is equal to x square raised to power 2, and x square is 16y, right? And here we have square. So here we can write 16y raised to the power 2, and here we have square root of 1 minus x square over 16, that is equal to y. So here we have y. For dx we can write 2 times y raised to minus half, and here we have dy, right? Okay, now see, here we have 16 square. So 16 square is 256. So we can write 256 outside the integral sign, and we can also take this 2 outside the integral, and now we have 0 to 1, and here we have y square. This is y square, and here we have y raised to minus half. So here we have half, and then square root of 1 minus y can be written as 1 minus y raised to half, and here we have dy, right? So now the product of these three numbers is equal to 2048, and we have 0 to 1, and this is y raised to 2 to the 4, 4 minus 1, 3. So we have 3 by 2, and 1 minus y raised to half, right? Okay, now we'll write it like this: 0 to 2048, then we have 0 to 1, and see, y raised to 3 by 2. Now we can express 3 by 2 as 5 by 2 minus 1, right? So why we are writing this like 5 by 2 minus 1? In order to convert this integral into the beta integral, right? And here we have 1 minus y raised to 3 by 2 minus 1, right? So now we have written y raised to 3 by 2 as y raised to 5 by 2 minus 1, and half as 3 by 2 minus 1. So now see, the beta function is defined like this: beta mn. We can write it as 0 to 1, and here we have x raised to m minus 1 and 1 minus x raised to n minus 1 dx, right? So where m and n are greater than 0, right? So the Euler's first integral is defined like this: the beta mn is 0 to 1 x raised to m minus 1 and 1 minus x raised to n minus 1. So if we compare this integral with this one, then we can see that the variable is y here, the variable is x here, and it is not going to change it. And here m is 5 by 2 and n is 3 by 2, right? So comparing, we have m is equal to 5 by 2 and n is equal to 3 by 2, right? So now this integral I can be written as 2048, and here we have beta mn. M is 5 by 2 and n is 3 by 2, right? So now we have to calculate the value of beta 5 by 2 comma 3 by 2, right? And we know this relation, that is relation between beta function and gamma function, that is beta mn is given by gamma of m multiplied gamma of n and divided by gamma of m plus n, right? So the beta of 5 by 2, 3 by 2 is equal to gamma 5 by 2. Then we have gamma here 3 by 2. And then we have gamma of 5 by 2 plus 3 by 2, right? Now see, in the denominator we have gamma of 5 by 2 plus 3 by 2, right? So this is 5 plus 3, 8 over 2, that is gamma of 4, and gamma of 4 can be written as 3 factorial, right? Because we know that gamma n plus 1 is equal to n factorial, where n belongs to some positive integer, right? So here we have 3 factorial. 3 factorial is 3 times 2 times 1, that is equal to 6, right? Okay, now to get the value of gamma of 5 by 2 and gamma 3 by 2, we'll make use of one important relation, that is gamma of n plus 1 can also be written as n times gamma of n, right? So gamma of 5 by 2 can be written as 3 by 2 times half times gamma of half, right? Due to this result. So we have 3 by 4 and gamma half is square root of pi, right? So the value of gamma half is square root of pi, and gamma of 3 by 2 can be written as half times gamma of half, and that is half times square root of pi, right? So viewers, the value of this quantity is now 3 by 4 square root of pi, and here we have half square root of pi, and in the denominator we have 6, that is 3 factorial, that is 6, right? So this is 3 divided by 4 times 2 times 6, and here we have square root of pi times square root of pi, that is pi. So this is 3 to the 6, so we have 4 times 2 times 2, that is pi over 16, right? So now the value of this integral I is equal to 2048 times beta of 5 by 2, 3 by 2, and this is 2048 times pi over 16, right? So the value of this quantity is pi over 16. Now if we divide 2048 by 16, we'll get 128, right? So we have 128 times pi, right? So the value of this integral using the concept of beta function and gamma function is 128 times pi, right?